Welcome to Lecture 5.1, Matrix Solutions for Linear Systems for Introduction to Programming in Mechanical Engineering. By the end of this lecture video, you will have an understanding of what a linear system is, how to format a linear system into matrix vector form, how to solve a linear system in matrix vector form, and the advantages of backslash notation for solving linear systems. This slide, the table of contents, contains hyperlinks to each of the sections to make the downloaded PDF easy to navigate. A system of equations is defined by two or more equations with two or more unknown variables. A linear system is linear with respect to the unknown variables. For example, the system 2x plus y equals 10 and x plus y equals 6. This system contains two equations and two unknowns. Every equation in a linear system represents a constant plane in the space of the unknown variables. In our example with two equations, x and y are the two unknown variables. So both equations represent a quote-unquote plane in two dimensions, or in other words, a line. The intersection point, if it exists, of those quote-unquote planes is the solution to the system. Let's take a look at this with our system of two equations. Here we see the graphs of both lines in the system. The line 2x plus y equals 10 is drawn in green, and the line x plus y equals 6 is drawn in blue. The intersection point, labeled with red at the point 4, 2, is the solution to the system. Now consider the following three-dimensional system of equations. 2x plus y plus 3z equals 10, x plus y plus z equals 6, and x plus 3y plus 2z equals 13. Here, each equation represents a planar surface in xyz space, which is three-dimensional. Again, let's look at a graphical representation of this system. Here we see the graphs of all three planes in the system. These planes are a close approximation, but note that they are not perfectly to scale. Now, this representation is harder to interpret than the two-dimensional case, so let's break it down a little bit. We remove the magenta plane so that we can just see the blue and the green planes now. Then we highlight the line at which they intersect with each other. Now, if we do the same with the blue and the magenta planes, we again highlight their line of intersection, and finally do the same with the green and magenta planes, highlighting their line of intersection. If we return now back to the view with all three planes and break it up by their corresponding overlaps, we see a singular intersection point, which represents the solution to the system of equations. This tangent that we have just gone down gives us a physical sense for what linear systems of equations actually represent. And with that comes a more intuitive understanding for what it means to actually solve the system, which is that if a solution exists, each variable together represents a coordinate in n-dimensional space that is the intersection of all the quote-unquote planes in the system. This lecture will focus on using matrix vector form to solve the system of equations, which will require rewriting the equations into that form. For the three-dimensional example we've been working with, this is how that would work. The coefficients for the variable x in all three equations form the first column of a coefficient matrix, and the variable x is then the first entry into the variables vector, which must be a column vector. Then the coefficients for the variable y in all three equations form the second column, and the variable y is then the second entry into the variables vector. And finally, the coefficients for z in all three equations form the third column, and the variable z is then the third entry into the variables vector. Then finally, a column vector is populated with the constants from each equation on the right-hand side of the new matrix equation. Altogether, the whole system of equations is converted into the following matrix vector relationship. This matrix vector form is equivalent to the original system of equations. We can see this by following the rules of matrix vector multiplication. Starting with the first row of the coefficient matrix, each element is multiplied by its corresponding variable in the variable's column vector. As you can see, this completely recovers the original first equation. The second equation is recovered in the same way, using the second row of the coefficient matrix, and the third equation is the exact same process again, but with the third row of the matrix. Altogether, we see that the matrix multiplication returns the exact same original three equations. They are mathematically equivalent to each other. Now, before we move on, we have to take a slight detour to motivate what we'll do next in the linear system. Consider how you would solve for x in the following equation, a times x equals b. By algebra, we just divide by a to get that x equals b divided by a. Now, returning to the linear system, each part of the matrix vector form of the equation is labeled as follows. The coefficient matrix is labeled as a, the variables vector is labeled as the vector x, and the right-hand side vector is labeled as the vector b, or in short form, a times x equals b. Just like with simple algebra, this system can be solved by moving a over to the right-hand side. But unlike normal algebra, we can't simply divide by a. Matrices cannot be divided. Instead, we have to invert the matrix. Here, we have the coefficient matrix colored in blue. To solve for the values in vector x, we invert the coefficient matrix to move it to the right-hand side, and then the vector b is multiplied after that. Note that because the matrix is initially positioned to the left of the x vector, its inverse should also be positioned to the left of the b vector. The hardest part here is inverting the matrix. The inverse of our coefficient matrix is given here. This is a programming course, so I just used MATLAB here, which will be shown later, but there are plenty of methods for inverting matrices by hand, one of which is linked here in the downloaded PDF. Feel free to read more into it if you're interested. With the inverse of the matrix calculated, we can actually solve the system with the following matrix multiplication. To solve for x, consider the first row of the matrix multiplied by the b vector. X is equal to -1 times 10 plus 7 times 6 plus -2 times 13 all divided by 3, which is equal to -10 plus 42 plus -26 all divided by 3, which is equal to 6 divided by 3, which is equal to 2. Y is equal to -1 times 10 plus 1 times 6 plus 1 times 13 all divided by 3, which is equal to -10 plus 6 plus 13 all divided by 3, which is equal to 9 divided by 3, which is equal to 3. And z is equal to 2 times 10 plus -5 times 6 plus 1 times 13 all divided by 3, which is equal to 20 plus -30 plus 13 all divided by 3, which is equal to 3 divided by 3, which is equal to 1. And with that, the solution is given in the following vector. xyz is equal to 2, 3, 1. There are better methods for solving a linear system than explicitly inverting the matrix and doing the matrix vector multiplication. Cramer's rule, Gaussian elimination, and LU decomposition are some of them, all of which are linked here in the PDF if you're interested in reading more. We won't cover these in detail because that's a discussion for a linear algebra course, but it is valuable to understand them nonetheless. Some advanced coursework may even expect you to implement some of them in code yourself, but for now, we get to use MATLAB to do the whole thing for us. First, we define the coefficient matrix. A variable coefficient matrix stores that matrix. Note that here each element of each row is separated by commas, and each row is separated by a semicolon. The ellipses at the end of the first two lines are used to split the matrix onto new lines. This is helpful for visual formatting, but it is not necessary as it can be defined all in one line. And remember that this matrix should be square for a properly constrained system. Then define the right-hand side vector, which we previously called b. Recall that this should be a column vector, and therefore the elements of this vector should be delimited by semicolons. And finally, we can solve the system by computing the inverse of the coefficient matrix using the inv command and multiplying by the right-hand side vector. This prints the output vector 2, 3, 1, just like we calculated previously. Here, the inv command was used to evaluate the inverse of a matrix. You can achieve the same result by raising the matrix to the power of -1, but the recommended approach to actually solving linear systems is to use the backslash operator instead, as shown here, a\b. Backslash notation automatically solves a linear system like we saw earlier, that is ax equals b. This is recommended over writing inv a times b or a to the -1 times b because it is significantly faster. The MathWorks documentation linked here will describe the backslash operator in more detail, but we will run an experiment to highlight the speed difference between them. First, we declare n as the number of unknowns in the system. We'll use 1e3, which is equal to 1000 for the number of elements. Then we define the coefficient matrix A as just some random matrix with dimensions n by n so that it is square. And then we define the n by 1 vector of quote-unquote unknowns. This is necessary to solve for b in the next step, which we'll use to backsolve. Then we solve for b by multiplying a times x. This will again be used to backsolve for x for the actual test. Next, we start a timer to evaluate how long the system solution takes using the explicit inv command. Then we solve the system using that command just like we did before, and then we close the timer using the talk command. Then we can start a timer using the backslash notation, and then use backslash notation to solve the system, and then we close the timer again using the talk command. Now the values of these two timers in seconds are given as follows. The time for using the inverse command is 0.0519 seconds. The time for using the backslash operator is 0.0207 seconds. The ratio between these times is calculated as follows. The inverse time elapsed divided by the backslash time elapsed gives 2.5050. This tells us that for this example, using a backslash b is 2.5 times faster than inv a times b. When looking to evaluate just the inverse of a matrix, the inv a command, or raising to the power of -1, can be sufficient. But for actually finding the solution to a linear system, it is faster and more reliable to use backslash notation. For small systems, though, the time that it takes to solve the system may be negligible either way that you choose. Now, useful for some more advanced problems, backslash notation can actually solve over constrained systems where the number of equations is greater than the number of variables. In contrast, the inv command will error if a is not square, even if there might be a solution for the over-constrained case. You may not always be solving properly constrained systems, so it is good practice to always use backslash notation. Now, in summary, a linear system is a set of n equations with n total unknown variables. The solution to that system is the intersection point in n-dimensional space between each quote-unquote plane in the system. Formatting a linear system into matrix vector form is done by arranging each equation with the unknowns in the same order, and then the coefficient matrix is composed of the coefficients for each variable in each column of that matrix. The variable's column vector contains all of the unknowns in the same order as they appear in each equation, and then finally the right-hand side vector contains the constants from each equation. We use MATLAB's built-in inv a times b, or the backslash notation a backslash b, to find the solution to the linear system. And for the advantages, it's faster to use backslash notation than the inv command, and it can also solve over constrained systems, and it's more reliable as a result with systems with high condition numbers, as you can find in the documentation if you are interested.